In this video, I'll cover first-order logic. I'll go over the basic elements of first-order logic, and then show how sentences can be converted to first-order logic. Then I'll discuss the semantics of first-order logic before working through an example of checking sentence validity. I'll close with a brief discussion of inference. First-order logic is a meaning representation language that satisfies many of the previously defined requirements of verifiability, inference, and expressiveness. Its representations make use of the fundamentals of model-theoretic semantics, objects, properties, and relations. The basic logic device in first-order logic is the term, which represents objects. Terms can be represented using constants, functions, or variables. Each term, regardless of whether it's a constant, function, or variable, can be thought of as a way to specify a particular object in the world. Breaking down the different types of terms into a little bit more detail, constants are specific objects in the world being described. You'll generally see constants represented as capital letters or natural language words, and each constant refers to exactly one object. Functions are similar to single argument predicates. They can refer to specific objects without associating a named constant with those objects. For example, although Chicago would be a constant, location of Giordano's would be a function. Variables do not refer to a specific object, but rather to one or multiple anonymous objects. Their use makes it possible to make assertions and draw inferences without having to refer to a specific named object. Variables are generally depicted as single lowercase letters. In first-order logic, as already briefly mentioned, there are also predicates which generally refer to the relations between objects within the domain. Predicates can have one or more arguments and can be connected with one another using logical connectives or other operators, such as the and or operators, the implies connective, or the negation operator. Two basic operators in first-order logic are the symbols shown here. The one that looks like a backwards E is the existential quantifier and means there exists. The one that looks like an upside-down A is the universal quantifier and means for all. These two operators are extremely useful when trying to represent things equivalent to each and every. For example, we can represent a single anonymous restaurant by saying there exists a variable X for which X is a restaurant. We can represent the set of all restaurants by saying for all variables X, X is a restaurant. This brings us back then to the example from the previous video, where we had some complex sentences like what you see on the right here, and weren't sure how to represent them. In first-order logic, we can represent complex sentences by combining basic elements using connectives and other operators. So to convert the sentence, Nicholas likes Giordano's and Usman likes Artopoulos to first-order logic, we could take the predicate Nicholas likes Giordano's and the predicate Usman likes Artopoulos and join them with the and connective. To convert the sentence Mina likes fast restaurants to first-order logic, we could say that for all X where X is fast, the predicate Mina likes X is implied. Finally, to convert the sentence, not everybody likes IDOF, we could say that there exists a variable X, such that X is a person and X does not like IDOF. Once we're able to do this, we're able to evaluate the semantic truthfulness of a wide range of sentences. In fact, hopefully all sentences in our language. We do this based on truth conditional mappings between our meaning representations and the facts that we know about the world being modeled. Specifically, we can determine truth as indicated by a meaning representation based on the presence of specified terms and predicates. For example, if P is false, then not P is true. And if P and Q are individually false, then P and Q connected using a logical and are false, as are P and Q connected by a logical or, but P implies Q is true. The full truth table for the basic set of terms and corresponding logical connectives is provided here. We can work through an example to see what this process of determining sentence validity would look like. We'll start out with the same model we used in the previous video. If you're watching these videos out of order, you may want to pause and watch the video on model theoretic semantics to review. Basically, we have a restaurant domain where we know some specific patrons, restaurants, and cuisines, and we know a few properties like which restaurants are fast and which restaurants provide table service. And we know a few relations like which patrons like which restaurants and which patrons serve which cuisines. In this example, we're going to determine whether the sentence Natalie likes Giordano's and Usman likes Giordano's is valid according to our model. To determine this, we'll first convert the sentence into first-order logic. It looks like we'll need to set up two likes relations, one for our patron Natalie liking Giordano's and one for our patron Usman liking Giordano's, and then connect them using a logical AND. We'll replace the full named values with the constants that represent them. Then we'll start checking the truthfulness of the individual statements. We'll start with A likes E. We see that that's included in our list of facts we have about who likes which restaurants, so the value for this predicate is true. Next, we'll check for B likes E. It looks like that predicate isn't included in the list of who likes which restaurant, so its value will be false. This means we'll be taking the AND of a true value and a false value. We know from our truth table that the output of this will be a false value. So the sentence is not valid according to our model. There are a couple extra things to keep in mind when dealing with the existential and universal quantifier. Formulas that include the existential quantifier are true if any term that could be substituted for the variable would result in a true value. And formulas that include the universal quantifier are true only if all terms that could be substituted for the variable would result in a true value. Sometimes we'll need to check the veracity of input that isn't explicitly provided for in the knowledge base. When we need to do this, we can try to infer the necessary facts using a process called modus ponens, or if-then reasoning. Basically, if we have a predicate P and a predicate Q, and we have a conditional statement if P then Q that has been accepted as true, and we also know that P is true, then we can also infer that Q is true. More generally, we can infer that the right-hand side of an implication is true if we know that the left-hand side of the implication is true. We can see what this looks like here. Let's say that we have a function, Greek restaurant Artopolis, and we also have a conditional statement for all x, where x is a Greek restaurant, x serves Greek food. The conditional statement has been accepted. We check the antecedent and it holds, so our model says that Artopolis is indeed a Greek restaurant, making the value true. This means that we can infer that the consequent Artopolis serves Greek food can be inferred as being true as well.